Section 7.2 of your textbook covers the substitution method for solving systems of equations. Remember that a system of equations is a set of two or more equations that are to be solved simultaneously. A solution of the system must also be a solution of every equation in the system. We've already discussed the graphing method for solving systems. The substitution method is an algebraic process that does not require drawing a graph. To solve a system of two linear equations by substitution, we will use 4 steps. First, isolate one variable in one of the equations. Second, in the other equation, substitute the equivalent expression for that variable. Third, solve the resulting equation to find the value of one variable. And fourth, substitute this value into one of the equations to find the value of the other variable. Our first example is shown on the slide. For ease of reference, let's call x plus 3y equals 1, equation number 1, and y equals 2x plus 5, equation number 2. Note that the second equation of our system, y equals 2x plus 5, already has y isolated, so we're finished with step 1 of our substitution process. Moving to step 2, we substitute the expression 2x plus 5 in place of y in equation number 1. This means we have x plus 3 times the quantity 2x plus 5 equals 1. Now moving to step 3 of our process, we'll solve this equation for x. First, apply the distributive property, x plus 6x plus 15 equals 1. Next, combine like terms, 7x plus 15 equals 1. Now subtract 15 on both sides, 7x equals negative 14. And finally divide both sides by 7 to obtain x equals negative 2. So we found the value of x. Now step 4 is to substitute this value back into one of the original equations to find the value of y. In this case, the easiest substitution to make would be into equation 2, since y is already isolated in that equation. So we have y equals 2 times negative 2 plus 5, or y equals negative 4 plus 5. Therefore, y equals 1. So the solution of the system is x equals negative 2, y equals 1. Remember that this can be written as an ordered pair, negative 2, 1, indicating that if we were to solve this system graphically, by graphing each of these two equations, we would see two intersecting lines, intersecting at the point negative 2, 1. Let's look at some more examples of the substitution process. In problem number 1 on this slide, we'll have equation number 1, x equals 9y minus 4, and equation number 2, 7y minus x equals 10. Note that in this case, x is isolated in equation number 1, so we'll begin by substituting in for x in equation 2, so that we have 7y minus the quantity 9y minus 4 equals 10. In this case, we're going to solve for y first, and then solve for x after that. Solving the equation for y, we see that y equals negative 3. Now substituting back into equation 1 to find x, we see that x equals negative 31. Therefore, once again, we have a single ordered pair as the solution of our system. In this case, the ordered pair negative 31, negative 3, again indicating that if we were to graph these equations, we would see intersecting lines. Let's look at example number 2. 6x minus 2y equals 16. We'll call that equation number 1. 5x plus y equals 8. We'll call that equation number 2. In this case, neither equation has one of the variables isolated, so we need to perform that first step of the substitution process. The easiest equation to work with would be equation 2. We can isolate y simply by subtracting 5x on both sides of that equation. So our new version of equation 2 is y equals negative 5x plus 8. Now that it's been rewritten, we can substitute in 4y in equation number 1 to obtain 6x minus 2 times the quantity negative 5x plus 8 equals 16. Now we solve this equation for x. So we have x equals 2, and we can substitute back into equation 2 to solve for y. So y is negative 2. Therefore, the solution of our system is the ordered pair 2, negative 2, indicating that, yes, again, we have two lines intersecting at one point. Let's look at two final examples to see what happens when we apply the substitution method to a system that has either no solutions or an infinite number of solutions. In problem 3, equation 1 is 2x plus 4y equals 8, and equation 2 is 3x plus 6y equals 9. Notice that we have neither variable isolated, so that's the first step. Let's take equation number 1 and solve for x. First step is to subtract 4y on both sides, so that we have 2x equals negative 4y plus 8. And the second step is to divide both sides by 2, so that we have x equals negative 2y plus 4. Note that when dividing by 2 on the right-hand side, we divided both terms by 2. Now that we've isolated x, we can substitute into equation 2. So we have 3 times the quantity negative 2y plus 4 plus 6y equals 9. To solve for y, we would first need to distribute. And then if we combine the like terms on the left-hand side, negative 6y plus 6y is 0. Those terms cancel out. So we have the equation 12 equals 9. This equation is always false. There are no values of x and y that would ever make this equation true. Since we have a false equation, we say that our system has no solutions. This is the case anytime we try to solve a system and obtain an equation that is always false. If we were to graph these two equations, we would see parallel lines. Finally, let's look at system number 4. X equals y plus 7 is equation number 1. 3y equals 3x minus 21 is equation number 2. In this case, equation number 1 has x isolated already, so let's just substitute into equation 2 to obtain 3y equals 3 times the quantity y plus 7 minus 21. Applying the distributive property, we have 3y equals 3y plus 21 minus 21. We can cancel out those constant terms on the right, so our equation is simply 3y equals 3y. And next, if we wanted to isolate the variable y, we would normally subtract 3y on both sides to get our like terms onto the same side of the equation. But if we do that subtraction, we would obtain the equation 0 equals 0. This is an equation that is always true. What this means is that we have a system that has infinite solutions. In such cases, our two equations in our system are actually equivalent equations, and so the graph would be one single line, as each equation has the same graph.